Hello and welcome to the third video of the FP1 chapter Proof. Quick starter question here. Find the first 5 terms of the recurrence relation. Un plus 1 is equal to 2 times un plus 5. N must be equal to or greater than 1 and u1 is equal to 3. So we've got the first one. We know that u1 is equal to 3 as part of the definition. We need 4 more. u2, the next one, is equal to 2 times u1 plus 5, so that's 2 times 3 plus 5 gives us 11. u3, following the same pattern, is 2 times u2 plus 5, 2 times 11, 22 plus 5, 27. u4, 2 times u3 plus 5, 2 times 27, 54 plus 5, 59. And the last one, 2 times u4 plus 5 is equal to 2 times 59, 118 plus 5, 123. In this video, we're going to prove general terms like the nth term for recurrence relations. And there's a quick note here before we get into the examples. Proof by induction is all the same, but if you have more initial values for n than just n equals 1, you should use the basis step to prove that all of them are true. So we're going to have a few more things to do in the basis step here, because as part of our recurrence relations, they're giving us more information. We need to check that it is all true, it all works. So as we go in, we'll be aware of that, because we're going to go right into the basis step for this example. Given that un plus 1 is equal to 3un plus 4, where u1 is equal to 1, we're trying to prove that the general statement, the nth term un, is equal to 3n minus 2. So the statement here is that this can be written as this. First, we need to prove that it will work when n equals 1. So that's u1, which we've been given is a 1. We need to prove that this is still true in the nth term. So with the nth term, that would be 3 to the 1 minus 2, which is 3 minus 2, which is 1. So that's fine. But we also need to prove the recurrence relation gives us a term that is true. So u2, which is 3u1, because we're using this in this to get u2, we need to prove that it works for n equals 2 here, which is n equals 1 here. So u2 from the recurrence relation is 3 times u1, which is a 1, plus 4, gives us a 7, and u2 in the nth term would be 3 squared minus 2, which is 9 minus 2, also 7. So we can say it is true for n equals 1 and n equals 2. Carrying on as normal then, we need to assume the thing we're trying to prove, i.e. this statement, is true when n equals k. So assuming that is true, we need to now prove that this general statement is true for n equals k plus 1, and that would be this. But in order to do this, in order to get this statement here, to show that this is true, we need to have a k plus 1 on the left, obviously. From this starting point then, I'm going to put n equals k in here in order to get k plus 1 term on the left. So I'm starting with uk plus 1 in the recurrence relation, because I've been given that this is true. And that uses the uk term because of how recurrence relations work. And from here, I'm going to substitute in this assumption to prove that if this is true, then this is also true. So I just go ahead and put that in. 3 to the k minus 2 plus 4, expand this out. We get 3 lots of 3 to the k, minus 6 plus 4, and using my indices rules, I can put that 3 in to 3 to the k plus 1, and minus 6 plus 4 is obviously minus 2. So we can say that if this statement here is true, then this statement is also true. And then don't forget your conclusion step in the end. Putting these two statements together, we can then say it must be true for all n where n is a member of the natural number set. Second and final example takes it one step further. Here we've got two starting conditions, u1 is equal to 13, u2 is equal to 35. We need to show that both of these are true in the nth term we're trying to prove. And we also need to show that the recurrence relation, which will give us u3, is also true in the nth term. So all of that happens in the basis step. u1 we've been given is 13, and in the nth term that would be 2 to the 1 plus 1 is 2 squared, 3 to the 1 plus 1 is 3 squared, is also 13. For u2, which we've been given is 35, the nth term would be 2 cubed plus 3 cubed, 8 plus 27, which is indeed 35. And then u3, which is the first time we've used the recurrence relation, 5 times u2 minus 6 times u1. If you put that on your calculator, you get 97. And in the nth term, u3 needs to be 2 to the power 4 plus 3 to the power 4, which is 16 plus 81, also 97. So this is true for n is equal to 1, 2, and 3. Now our assumption step. We're assuming that uk is equal to 2 to the k plus 1 plus 3 to the k plus 1. And we want to prove that uk plus 1 is equal to 2 to the k plus 1 plus 1. So that might look like k plus 2 when I get there, plus 3 to the k plus 1 plus 1, and again that might look like k plus 2 when I finish my working out. Now, we need a k plus 1 on the left, so in order to get that out of this statement, I'm going to need to use n equals k minus 1. So I've got u k plus 1 is equal to 5 times the term before that, so that's uk, that's fine, we've assumed something about that, minus 6 times the term before that. Now I need to assume something about this as well, and I think in the textbook they do it slightly differently. They prove it for k plus 2, they use k plus 1 here and k here, but you get hit with the same problem. You're using two terms to prove this, so you need to make an assumption about two terms. I've made this assumption already, that's fine. I'm going to make an assumption about this as well. So we're also going to assume that this nth term statement works for the term before the one I want. And that would make it 2 to the k plus 3 to the k if you put k minus 1 in here and here. So assuming this and assuming this, I'm going to prove this. And if this is true when these two are true, that's fine because I've done that here. This is true when these two are true. So putting all of that into this statement here, we've got 2 to the k plus 1 plus 3 to the k plus 1 minus 6 times 2 to the k plus 3 to the k, and then we've got a bit of algebra, expand this out. Then use my indices rules in order to get these so that they can interact. I'm going to want 2 to the k and 2 to the k, so I'll pull one of these 2's out the front and make that a 10. Same with this one, pull a 3 out, make that a 15, so I get 3 to the k. Then I can put these together, and that will give me 4 lots of 2 to the k, and 9 lots of 3 to the k, and 4, of course, is 2 squared, and I can put that into the index here and have 2 to the k plus 2. And 9 is 3 squared, so I can do the same thing here. And that is what I want, k plus 1 plus 1, to make it really clear what I've done. K plus 1 plus 1, and this is k plus 1 term. So now we can say that this nth term is true for n equals k plus 1 if it's true for n equals k, and if it's true for n equals k minus 1. Or, if you prefer the way the textbook has done it, then it's true for n equals k plus 2 if it's true for n equals k plus 1 and n equals k. Either way, we have proven that over here it is true in the case of the first 3 terms, therefore it must be true for the next 3, u2, u3, u4, and it must be true for the next 3, and so on and so on. So we have proven that this is true for all n where n is an element of the natural number set. And I hope that is enough for you to have a go at questions in exercise 8c, and maybe I'll see you for the final video of the module to apply this proof by induction method to matrices.